LinkedIn once pushed over 7 trillion messages in a single day, and at peak, that cluster was absorbing more than 7 million messages every second. What makes that number almost absurd is the hardware behind the right benchmark. 2 million records per second sustained on just 3 commodity machines. Not custom silicon, not a proprietary distributed file system, 3 cheap servers off the shelf. So the question worth asking is, what was everyone else doing wrong? Because if you've built a message queue before, you know that scaling one is not straightforward. Let's start with the design most engineers reach for first. You have a queue, a single ordered list of messages sitting on one broker. Producers append to the tail, consumers read from the head, and a pointer tracks how far each consumer has gotten. Simple, correct, and completely fine at a few thousand messages per second. Now add load. You bring 10 producers online, all hammering the same broker at once. Every write has to grab the queue's append lock, write its message, then release. 10 producers means 10 threads competing for one lock. The second producer is already waiting while the first finishes. This is a serialization point, and a serialization point means your total throughput is bounded by how fast a single thread can turn over that lock. Adding more producers does not increase throughput, it increases contention. You are not parallelizing work, you are serializing it more aggressively. The lock is not even your worst problem. Traditional brokers that ack and delete individual messages must do more than append. They update the queue head pointer, mark messages as consumed, write tombstones for deleted entries. Each of those is a small random update scattered across the data file. On a spinning hard disk, random I/O tops out at roughly 100 to 200 operations per second. That is not 100,000, that is 100. Even with generous OS buffering that pushes you to a few thousand, you hit the ceiling well before you approach any serious production traffic. SSDs improve the story, but they do not fix it. Even with tens of thousands of random I/O operations per second available, the serialization overhead and per message ACK cost keeps you far below 1 million messages per second. The disk itself becomes the floor that you cannot break through. Now you try scaling the other direction, more consumers. You add more reader threads, thinking parallel consumption should at least drain the queue faster. But all those readers still share the same offset pointer, which means they share the same lock. More consumers means more threads fighting over the same state, and throughput actually degrades. There is no horizontal lever here. Neither the write side nor the read side can be parallelized without breaking the single queue abstraction. So you are stuck with a design that has one bottleneck on writes, one bottleneck on reads, and a disk I/O model that punishes anything other than purely sequential access. The fundamental problem is architectural. One queue means one serialization point, and one serialization point means one throughput ceiling, no matter how fast your hardware is. The question then is whether you can serve millions of producers and millions of consumers simultaneously, truly in parallel, without any single broker, lock, or file becoming the global gate. Kafka's answer is to stop thinking of a queue as one thing. Instead of one ordered log shared by everyone, you split it into n independent append-only logs, each one owned by a different broker, written to by a dedicated set of producers, and read by a dedicated consumer. Those independent logs are called partitions, and everything Kafka does, speed, durability, horizontal scale, flows from that one structural choice. In Kafka, everything starts with a topic, a named logical feed for a particular category of events. You might have a topic called user clicks, another called payment events, another called order updates. But a topic on its own is just a label. The real structure lives underneath in the partitions. When you create a topic, you choose how many partitions it has, say 6. You can increase that number later if your traffic grows, but you can never decrease it. That one-way door matters, so plan your partition count carefully at creation time. Now, what exactly is a partition? Each partition is an ordered, immutable, append-only commit log. Messages arrive, they get written to the end of the log, and they stay there exactly where they landed. You never modify a message in place, you never delete one individually. The log only ever grows at the tail. Picture a scroll of paper that you can only write on at the bottom, line by line. Every new message goes on the next blank line, in the exact order it arrived. That scroll is a partition. This append-only property is not a limitation. It is the design choice that makes almost everything else in Kafka fast. Now, why does splitting a topic into multiple partitions matter so much? Because the partition is Kafka's unit of parallelism. Each partition can live on a completely different broker. Different consumers can read different partitions at exactly the same time, simultaneously, with no coordination between them. If you have 6 partitions spread across 3 brokers, you have 6 independent write paths and 6 independent read paths all running concurrently. That is the horizontal lever that a single queue design never had. There is one important constraint to understand about ordering. Kafka guarantees message order only within a single partition. Across partitions of the same topic, there is no ordering guarantee at all. If you write message A to partition 0 and message B to partition 1, there is nothing stopping a consumer from reading B before A. If strict global ordering matters for your use case, you must use a single partition. But that sacrifices the parallelism entirely. For most workloads, per-key ordering is enough, and Kafka lets you achieve that cleanly, as we'll see in the next part. Let's go a level deeper and look at what a partition actually looks like on disk. On the broker's file system, each partition maps to a directory. The directory name follows the pattern, the topic name, a dash, and the partition number. So partition 0 of user clicks lives at a folder called userclick0. Inside that directory, Kafka does not store one giant file per partition. It splits the data into segment files. Each segment is a group of 3 files sharing the same base offset as a file name prefix. The first file is htLog. This is the raw binary message data, the actual bytes appended sequentially. The second is hindex. This is a sparse index that maps a logical offset number to the physical byte position inside the htLog file. Because of this index, Kafka can jump to any specific offset in O of 1 time, no scanning. The third is hTimeIndex. This maps timestamps to offsets, enabling time-based lookups, useful when you want to replay messages from a specific point in time. At any given moment, only one segment in the partition directory is active, the one currently being written to. When that active segment reaches log_oled.bs, the default is 1 GB, Kafka closes it and rolls a new one. The old segment is now sealed. Old sealed segments are the unit of retention as well. When it's time to clean up, Kafka deletes or compacts entire segments as a unit. That makes deletion O of 1 regardless of how many messages a segment contains. Kafka never needs to scan individual messages to age them out. Now watch what happens when a new message actually arrives. The producer sends it to the partition leader. The leader appends it to the tail of the active.log file, a single sequential write. At the same time, it assigns the message a monotonically increasing integer called an offset. The first message in the partition gets offset 0. The next gets offset 1, then 2, 3, incrementing by exactly 1 with every append. That offset is the message's permanent address inside the partition. Stable, never changing, even after older messages have been deleted by retention. Watch the offset counter tick up with each append. This is the heartbeat of Kafka's log. Each tick means a message has landed, been assigned its permanent ID, and is ready to be read. Here is an important point about how this maps to writes. Since every append goes to the end of the same file, the disk head never needs to seek. It just keeps writing forward. That is pure sequential I/O, and it's why Kafka can write at speeds that approach the raw sequential throughput of the disk itself. The data structure is almost offensively simple, and that simplicity is deliberate. An ordered log, immutable entries, a monotonic offset counter, sparse index for fast seeks, segment-level cleanup. Each piece earns its place. So now you understand the structure a producer is writing into. The natural next question is, how does the producer decide which partition to send each message to? And how does it batch messages to make the most of that sequential write path? That is exactly what we'll cover next: key hashing, sticky batching, and compression. The answer to that question depends on one thing: whether your message has a key or not. If you set a key on your message, Kafka applies the murmur2 hash function to that key. It then takes the result modulo num partitions. That formula, murmur2 key %num partitions, is completely deterministic. Every message with the same key will always land on the same partition, every single time. That's how Kafka preserves ordering on a per-key basis. Order IDs go to one partition, user IDs go to another, and within each partition, the sequence is guaranteed. Now, what if you don't set a key? Before Kafka 2.4, the default behavior was round robin. Send one message to partition 0, next to partition 1, cycle through them all. That sounds balanced, but it created a real problem. Each message ended up in its own batch. Tiny batches, one record each. Tiny batches mean lots of small network writes, higher per message overhead, and noticeably higher latency. Kafka 2.4 fixed this with the sticky partitioner, introduced as KIP 480. The idea is simple. Instead of bouncing between partitions with every message, the producer sticks to one partition. It keeps sending to that same partition until either batch.size is full or linger.ms expires. Then it switches to a different partition and does the same thing. The result is that each batch fills up properly before it's sent. You get larger, more efficient writes instead of a flood of tiny ones. The measured improvement is dramatic. P99 latency dropped to roughly 1/5 of what it was before. In one test with one producer, 16 partitions, and 1,000 messages per second, P99 latency went from 1,017 milliseconds down to 204 milliseconds. That's just from changing how partition selection works. No hardware change, no replication change, nothing else. Now both keyed and unkeyed messages flow into the same core structure, the record accumulator. The record accumulator is an in-memory buffer. It holds one deck per partition. As messages arrive, they accumulate in the deck for whichever partition they're targeting. The producer doesn't send immediately. It waits for one of two conditions. The first condition, the batch reaches batch.size bytes. The default value of batch.size is 16 kilobytes, specifically 16,384 bytes. The second condition, linger.ms elapses. The default for linger.ms is 0 milliseconds, which means send right away. But in production, you almost never leave it at 0. A typical tuning is somewhere between 5 and 20 milliseconds for linger.ms, paired with a batch.size of 64 kilobytes or higher. That small wait gives more messages a chance to accumulate before the batch goes out, and the payoff is significant. Once a batch is ready, either because it's full or because linger.ms ticked out, the producer compresses the entire batch and sends it as a single network write, not message by message. One write per batch for all the records it contains. And compression here is end-to-end, which is one of the cleverer design choices in Kafka's architecture. The producer compresses the whole batch before it leaves the client. The broker receives that compressed batch and stores it compressed, exactly as is. When a consumer fetches that batch, it arrives compressed, and the consumer decompresses it on its side. The broker never decompresses the data at all. That means the broker spends zero CPU on the compression path. The work happens at the producer and consumer, which are often the machines that have spare capacity anyway. The choice of codec matters, and each one has a different trade-off. gzip gives you the best compression ratio, roughly 5 to 6 times smaller, but it's the slowest and most CPU intensive. Snappy, originally from Google, gives a moderate ratio of about 2 to 3 times, with much lower CPU cost and fast encode and decode speed. LZ4 offers a similar ratio to Snappy, but with even faster compression and decompression. It's the preferred choice when you care most about low latency. ZSTD is the newest addition, brought into Kafka 2.1 via KIP 110, and it arguably offers the best overall balance. Compression ratio that matches or beats gzip at speeds closer to LZ4. In practice, LZ4 and ZSTD are the two most common choices in high-throughput production systems. One more reason to favor larger batches. Compression ratio improves with batch size. When a batch is small, there's not much repeated content to exploit, but a large batch containing many messages with the same schema and similar header patterns gives the codec a lot to work with. Bigger batch, better ratio, fewer bytes on the wire, and lower per-message CPU overhead across the board. So to bring it together visually, messages stream into the record accumulator, filling up per-partition dequeues. Once a dequeue's batch hits batch.size or linger.ms fires, the producer compresses that entire batch and sends it as one network write to the partition leader. One batch, one write, one round trip, instead of dozens of individual messages chattering back and forth. That's how the producer side turns many small messages into a small number of efficient, compressed network operations. With the data now sitting on the broker, the question shifts to the consumer side. How does a consumer know where it left off, and how does it ask for the next batch? That's the job of offsets and the pull model, which is exactly what we'll look at next. The producer side is settled, but now comes the other side of the equation. How does anyone find a message, read it, and keep track of where they are? The answer starts with one of the most elegant ideas in Kafka's design, the offset. Every message written to a partition is assigned a monotonically increasing 64-bit integer, starting at 0. That integer is its offset, a permanent address stable for the lifetime of the cluster. And when I say permanent, I mean it. Even if older messages are deleted because they've aged out of retention, the offsets of the remaining messages don't change. Retention removes whole segments at a time, not individual records, so the numbering never shifts. Think of it like page numbers in a book that you can tear out from the front. The pages that remain still carry their original numbers. This stability is what makes offsets so powerful. You can always say, "Give me message at offset 4217, and Kafka knows exactly where to look. How? With the sparse index file, the .index alongside every .log segment. That .index file maps a logical offset to a physical byte position inside the .log. The seek is 01. Kafka doesn't scan the log, it jumps straight to the byte position and reads from there. So locating any message in a partition, regardless of how many millions of records are stored, takes constant time. Now, with addressing solved, let's talk about how consumers actually read. Kafka uses a pull model. The consumer polls the broker, asking, "Give me messages starting from this offset." The broker does not push messages out to consumers. This is a deliberate design choice, and it matters more than it might seem at first. Because the consumer controls the pace, it can read in large batches, fetching thousands of messages in a single request when it's running fast. It can also slow down, pause, or even rewind to an earlier offset without creating any pressure on the broker. The broker is oblivious to how fast or slow any consumer is. It just serves whatever is requested. Compare that to a push-based broker like RabbitMQ. There, the broker has to maintain a separate delivery rate for each consumer. If a consumer slows down, the broker must buffer outstanding messages somewhere, and that buffer can grow without bound. A single slow consumer can back-pressure the broker and hurt every other consumer sharing the same infrastructure. Kafka doesn't have that problem because the consumer owns its own position, and the broker holds no per-consumer state beyond what's been committed. So what does committed mean here? When a consumer finishes processing a batch, it commits its offset, telling Kafka, "I've processed everything up to here." That committed offset is stored in a special internal Kafka topic called Consumer Combating Offset. It's a compacted topic, meaning Kafka keeps only the latest committed offset for each consumer group, topic, and partition combination. By default, it has 50 partitions. The partition that stores a given group's offsets is chosen by #for_sex50, spreading load evenly across the cluster. Now, how you commit matters a lot. It directly controls your delivery semantics. The simplest option is auto-commit. With enable auto-committed equals true, Kafka commits your offset every 5 seconds automatically. It's convenient, but it carries a risk. If the consumer crashes after polling a batch, but before finishing processing, the offset may already have been committed, and those messages are lost. That's at most once delivery. Alternatively, if the commit fires after the crash, the consumer rereads and reprocesses, giving you at least once, but with potential duplicates. For safe at least once, you want manual commit with commit sync. You call commit sync after your processing logic completes, and it blocks until the broker acknowledges the commit. If the consumer crashes before that call, the offset is never committed, and the messages will be re-delivered on restart. There's also commit async, which doesn't block. It fires the commit and returns immediately. That's faster, but retries can arrive out of order, so you need to be careful with retry logic. And then there's the strongest guarantee, exactly once delivery. That's provided by the Kafka Transactions API, specified in KIP 98. You set a transactional.id on your producer, and on the consumer side, you set isolation lekeln to read committed. With that in place, a consumer only sees messages that were part of a successfully committed transaction. Partial or aborted writes are invisible. Exactly once is the right choice when your downstream cannot tolerate duplicates and idempotency isn't practical to build at the application layer. So, to put this all together, imagine the partition log laid out as a sequence of records, each labeled with its offset, 0, 1, 2, 3, advancing to the right. The consumer holds a pointer into that log. On each poll, the pointer advances by however many records were fetched. After processing, the consumer commits that new position to consumer offensive offset. On restart, it reads that committed position and picks up exactly where it left off. The pointer moves forward in lockstep with the consumer's processing. No broker involvement, no push, just a cursor that the consumer controls entirely. That's the pull model. Clean, stateless on the broker side, and endlessly flexible. One thing this model assumes is a single consumer per partition, and that's exactly where consumer groups come in. In the next part, we'll see how Kafka assigns partitions across a group of consumers, letting you scale reads horizontally without any one consumer becoming a bottleneck. Tracking offsets solves the "where am I" problem. But a single consumer reading millions of messages per second is still a bottleneck. What if you could split the work across multiple consumers? and have each one handle a slice of the traffic. That's exactly what a consumer group does. A consumer group is a set of consumers that all share the same group.id and collectively consume a topic together. The key rule is simple. Each partition is assigned to exactly one consumer within the group at any given time. So, if your topic has 3 partitions, you can have up to 3 consumers actively reading in parallel, 1 per partition. This is Kafka's horizontal scale-out story on the read side. And it's not just one group that can do this. Multiple independent consumer groups can read the very same topic simultaneously, each with its own set of offset pointers. One group might be your analytics pipeline. Another might be your search indexer, both reading the same events completely independently. This is the pub-sub pattern built right into Kafka's design. Now, there's a hard limit you need to know. The maximum useful parallelism inside a single group is min consumers partitions. If you have 3 partitions and you spin up a 4th consumer in the same group, that 4th consumer sits idle. There's no partition left to assign to it. If you need more throughput, the lever is to increase partition count first, then add consumers to match. So who manages all of this assignment and membership? That's the job of the group coordinator, a designated broker that Kafka selects by computing #vcove%numBrokers. The group coordinator tracks heartbeats from every consumer in the group, manages who joins or leaves, and triggers a rebalance whenever the group's membership changes. A rebalance is the process of redistributing partitions across the current set of active consumers. There are 4 main things that trigger one. First, a new consumer joins the group. Second, a consumer leaves, either gracefully or because it missed the heartbeat deadline set by session.time_timeout.ms. The default for session_timezone.ms is 10 seconds. Third, a new partition is added to the subscribed topic. Fourth, a consumer gets stuck in its processing loop and exceeds max_poll_timing.ms, which defaults to 5 minutes. Now, rebalancing sounds straightforward, but the original implementation had a serious flaw. The old approach is called eager rebalancing, and it works like this. The moment a rebalance is triggered, every consumer in the group stops consuming and surrenders every partition it holds. The coordinator then reassigns all partitions from scratch to all active consumers. This is a stop-the-world pause for the entire group. Even if just one consumer was added or dropped, every other consumer stops, and the group produces 0 throughput during the reassignment window. On a large group with many partitions, that pause adds up. Let's say you have 3 partitions assigned across 3 consumers. Consumer 3 goes down. Immediately, all 3 partitions are revoked. Consumers 1 and 2 stop as well. After the coordinator finishes reassignment, consumers 1 and 2 each pick up some partitions and resume. The whole group paid the cost even though only one member changed. Kafka fixed this in version 2.4 with KIP 429, the Incremental Cooperative Rebalance Protocol. The assigner behind it is called Cooperative Sticky Assigner. Instead of revoking everything at once, it uses a 2-round handshake. In round 1, the coordinator identifies only the partitions that need to move. In round 2, those specific partitions are handed off to their new owners. Crucially, consumers that are not affected keep consuming their current partitions throughout the entire process. So, in our 3 consumer example, consumer 3 drops out. Only the partitions that belong to consumer 3 are revoked and redistributed. Consumers 1 and 2 never stop. Instacluster benchmarked this and reported rebalances up to 20 times faster than the eager protocol in some scenarios. For groups with dozens of consumers and hundreds of partitions, that's the difference between a brief hiccup and a multi-second outage. So, to summarize the consumer group model, partitions are the unit of parallelism, one consumer per partition within a group, and the cooperative sticky assigner keeps rebalances surgical rather than catastrophic. Now that we know how Kafka scales horizontally on the read side, there's a deeper question. Why is each individual broker able to sustain such extreme throughput in the first place? The answer lives in three tightly coupled design choices: sequential I/O, the OS page cache, and zero-copy transfers. And that's exactly where we're heading next. Sequential disk I/O, the OS page cache, and a kernel trick called zero-copy. Those are the three interlocking design choices that explain why a single Kafka broker is so blazingly fast. Let's start with the one that sounds like a contradiction. Kafka writes to disk, and yet it's fast. To understand why, you need to know how differently disks behave for sequential versus random access. On a spinning hard drive, sequential read and write throughput sits around 100 to 200 megabytes per second. Random I/O on that same drive, jumping around to arbitrary byte positions, drops to roughly 0.1 to 1 megabytes per second. That's a 100 to 1,000 times gap just from access pattern. SSDs are dramatically faster overall, hitting 500 to 3,000 megabytes per second sequentially. But even on an SSD, random I/O lands around 50 to 400 megabytes per second, still a roughly 10 times gap versus sequential. The access pattern matters enormously on any storage medium. Kafka's append-only log is 100% sequential writes by design. Every new message goes to the end of the active segment file. The disk head never seeks backward. So Kafka doesn't fight physics, it works with it. Now here's the myth you should retire right now. Kafka is slow because it writes to disk. That is false. A sequential disk write on a modern OS can match or exceed random RAM access in raw throughput, because the OS doesn't actually touch the disk for every write. That's where the page cache comes in. When Kafka receives a message from a producer, the write lands in the Linux page cache, which lives in RAM. The OS marks those pages as dirty and flushes them to disk asynchronously in the background. From the broker's perspective, a produce request is essentially a write to memory. Now consider the read side. When a consumer fetches a message that was written a second ago, where is that data? Still in the page cache, which means the consumer reads from RAM too, with no disk access at all. On a healthy cluster where consumers are keeping up, disk read IOPS can be near zero. Multiple consumer groups reading the same partition all share the same cached pages. The OS fetches the data from disk once, then serves every subsequent read from RAM. This is fundamentally different from what you'd get with an in-JVM cache, and it's worth understanding why. An in-JVM cache adds GC pressure. Every cached object is one more thing the garbage collector has to scan and potentially move. It also evaporates on a JVM restart. If the broker process crashes and restarts, your warm cache is gone. The page cache, by contrast, survives a JVM restart completely. If the broker process dies and comes back up in 30 seconds, the OS page cache is still warm. Consumers resume at full speed. And the page cache scales automatically with however much RAM your machine has, with no configuration required. Now we get to the third layer. What happens when Kafka sends cached data across the network to a consumer? Without any optimization, the data path looks like this. The OS issues a read syscall, disk to kernel read buffer. That's copy 1. The kernel copies from its read buffer to your application's user space buffer. That's copy 2, plus a context switch from kernel to user space. Your application calls write, user space buffer to kernel socket buffer. That's copy 3, plus another context switch back into the kernel. Finally, the NIC DMA copies from the socket buffer out onto the wire. That's copy 4. Total, 4 data copies and 2 user-to-kernel context switches. And that overhead fires for every single fetch request. Kafka eliminates most of that with a Linux syscall called sendFile. Instead of bouncing data through user space, sendFile transfers directly from the page cache to the socket buffer descriptor inside the kernel. The NIC then DMA reads from that socket buffer onto the wire. Total, 2 copies, or just 1 if your NIC supports scatter-gather I/O. 0 user space context switches. In Java, Kafka calls this through file channel TRX2, which the JVM maps directly to sendFile on Linux. The impact of 0 copy isn't theoretical, it's been benchmarked. Without 0 copy, a Kafka broker handled around 450,000 messages per second. With 0 copy enabled, that same broker reached 1.85 million messages per second. That's a 4.1 times throughput improvement from one syscall change. CPU utilization dropped from 82% to 21%, a 3.9 times reduction. Context switches fell from 900,000 per second to 120,000 per second, a 7.5 times reduction. And P99 latency improved from 45 milliseconds down to 12 milliseconds, all from avoiding unnecessary data movement. The fourth ingredient is batching and compression, and they compose perfectly with everything above. Recall from the producer side, the entire batch is compressed end-to-end. The broker stores it compressed as is, and the consumer decompresses locally. The broker spends 0 CPU on the compression path, and because a batch is one contiguous blob in the page cache, 0 copy can transfer the whole thing in a single sendFile call. Batching, page cache, and 0 copy reinforce each other at every step. To visualize this, in the traditional path, you see 4 arrows crossing the user kernel boundary, each one a toll. In the 0 copy path, there are 2 arrows, both inside the kernel. The page cache hands data directly to the socket buffer. The NIC pulls it out, and the consumer gets it. Add the page cache warm read scenario on top. In a caught-up cluster, step 1 doesn't even need the disk. The data is already in RAM, waiting. So what you end up with is a design where the fast path is producer writes to RAM, broker reads from RAM, sendFile into socket, consumer receives. No disk head movement, no user space copies, no GC pauses, no broker CPU on compression. That's why a single Kafka broker can saturate a 10 gigabit per second NIC before it runs out of CPU. All of this speed is impressive, but you might be wondering, if Kafka is this aggressive about avoiding disk writes, what happens to your data if a broker crashes? That's exactly what the next part covers. How Kafka's ISR replication and Acks settings give you strong durability guarantees without giving back the throughput you just gained. Replication is how Kafka protects every message without giving back the throughput gains, and it's more thoughtfully designed than you might expect. Every partition has exactly 1 leader and R-1 followers, where R is the replication factor. In production, R is almost always 3. That means you can lose 2 brokers entirely and still have your data intact. Producers always write to the partition leader, never directly to a follower. The followers then pull from the leader asynchronously to stay in sync. This pull-based replication keeps the write path simple. The leader appends, the followers catch up. Now, not all followers are created equal at any given moment. Some may fall behind. Maybe a broker is under load, or there's a brief network hiccup. That's where the ISR comes in, the in-sync replicas. The ISR is a dynamic set. Only replicas that have caught up to the leader within the last replica.lag.time.max.ms are members. The default for replica.lag.time.max.ms is 30 seconds. If a follower falls too far behind, Kafka quietly removes it from the ISR. Only ISR members are eligible to become the new leader if the current leader fails. This is the key insight. By restricting leader election to ISR members, Kafka guarantees that no committed message is ever lost during a failover. Now, how does the producer control how strong this guarantee is? That's the Acks setting, and it has 3 levels. Acks equals 0 means fire and forget. The producer doesn't wait for any acknowledgement at all. Throughput is maximum, but if the broker drops the message, you'll never know. Acks equals 1 means the leader writes the message to its local log and acts immediately. That's fast, but there's a window of danger. If the leader crashes before any follower has replicated, that message is gone. Acks equals all, or -1, is the strongest guarantee. The leader waits until every ISR member has written the message before acknowledging the producer. Combined with the ISR guarantee, no write that receives an ACK can ever be lost. But Acks equals all alone isn't quite enough. You need to pair it with min in sync replicas. Here's why. If 2 followers fall behind and get removed from the ISR could shrink down to just the leader. At that point, Acks equals all is effectively the same as Acks equals 1. Min in sync.replicas prevents that trap. Set min in sync replicas equals 2, and Kafka will reject writes with a not enough replicas exception if the ISR drops below 2, failing fast rather than silently accepting data you could lose. The standard production triplet is replication.factor equals 3, min in sync.replicas equals 2, Acks equals all. This configuration tolerates one broker failure while still accepting writes, and it gives you the strongest durability guarantee Kafka offers. There's one more piece, the high water mark, or HWM. The HWM is the highest offset that has been written to all current ISR members. Consumers never read past the HWM. Any message the leader has received, but that hasn't yet been replicated to all ISR members, is invisible to consumers. This keeps replication transparent. Consumers only ever see committed, durable data. Now for the question you're probably asking. What does all this cost in performance? With Acks equals all in a well-tuned same data center cluster, replication typically adds just 1 to 10 milliseconds per write. And the proof is in the numbers. Confluence Benchmark sustained 605 megabytes per second with Acks equals all, replication factor 3, and min in sync replicas equals 2, running on EC2 i3 EN.2x large instances. Durability and throughput are not opposites. Kafka gives you both. With all these pieces in place, partitions, replication, ISR, and the HWM, let's now trace a single message end-to-end through the entire system. Let's follow one message all the way through, from the producer's send call on one side to the consumer's final commit on the other. Picture a swim lane diagram with 4 lanes: producer, broker leader, followers, and consumer. Everything starts on the producer side. The producer has a message with a key, let's say a user ID. Num partitions routes it to the right partition. That message joins the record accumulator until batch size fills or linger.ms fires. The batch is then compressed end-to-end, say with LZ4 or ZSSD, wrapped into a produce request and fired to the partition's leader broker. Now we cross into the broker leader lane. The leader receives the produce request. It appends the entire compressed batch as a single sequential write to the active .log segment on disk. That write lands in the OS page cache first, effectively writing to RAM. The leader then assigns monotonically increasing offsets to each record inside the batch. Offset 0 goes to the first record, offset 1 to the next, and so on. Stable, permanent addresses forever. Simultaneously, the leader starts asynchronous replication. Followers in the ISR begin fetching the new data. Now, the ACK path depends on what the producer configured. If Acks equal elem, the leader waits. It won't respond until every ISR follower has confirmed the write. Each follower fetches the batch, appends it to its own replica log, and sends back an acknowledgement. Once all ISR members have ACKed, the leader sends a produce response back to the producer, carrying the base offset of the batch. The producer records that base offset and considers the send complete. That's the write path closed. Now let's switch to the consumer lane, which has been running its own loop in parallel. First, the consumer checks in with the group coordinator broker to confirm its current partition assignment. Once it knows it owns, say, partition 2, it sends a fetch request to the partition leader for that partition. The fetch request says, "Give me messages starting at my current committed offset." Back in the broker leader lane, the leader handles that fetch request. It checks the high watermark, the HWM, which is the highest offset that all ISR members have confirmed. The consumer can only read up to the HWM. Uncommitted messages stay invisible. The leader looks for the requested data in the page cache. If the consumer is caught up, that data is almost certainly already in the page cache. No disk read needed. The leader calls sendFile to transfer the compressed batch directly from the page cache into the consumer's socket buffer. This is the zero copy path. The data never touches user space on the broker. No copy into a Java heap, no recompression. Just kernel to NIC in 2 copies or fewer. The consumer receives the compressed batch. It decompresses locally. The broker never had to do that work. The consumer processes each record in order. When it's done, it calls either commit sync or commit async to record its new offset. That commit is durably written to consumer ACNG, and the consumer's next fetch request picks up exactly where it left off. Now step back and look at what just happened in that entire sequence. Every single message goes through 2 operations that are non-negotiable: a sequential append on the write side and a zero-copy send file transfer on the read side. Those are the 2 hot path operations at the core of Kafka's throughput. And because they're both O1 and hardware-friendly, the per-message cost stays tiny no matter how fast you push. With that full picture in mind, let's step back and name the 4 pillars that made all of this possible. Every number you've seen in this video traces back to one of 4 pillars. The first pillar is partitions, and partitions mean parallelism. A topic isn't one log, it's n independent logs spread across n brokers. Add n consumers in a group, and each one owns its own slice of the data. That's how LinkedIn hit 2 million writes per second on just 3 commodity machines back in 2014. At production scale today, LinkedIn processes over 7 trillion messages per day across its clusters. That's not Kafka being clever, that's linear scale-out doing exactly what it promises. The second pillar is offsets, and offsets mean the consumer owns its position. Kafka doesn't push messages at you, you pull them at your own pace. Your offset is a simple integer, and it's yours to advance, pause, or rewind. Because consuming doesn't delete anything, a second consumer group can replay the exact same stream from scratch independently. There's no broker back pressure, no rate matching, no coordination tax. The third pillar is consumer groups, and consumer groups mean scale-out reads. Each partition is assigned to exactly one consumer within a group at any given time. Add more consumers and the partitions redistribute. More consumers means proportionally more throughput. But there's a ceiling. Max useful parallelism equals min of consumers and partitions. Beyond that partition count, extra consumers just sit idle. The lever to raise the ceiling is adding partitions, not adding consumers. The fourth pillar is sequential I/O plus zero copy, and that's raw speed at the OS level. Sequential writes mean Kafka's active segment is one long append, never a random seek. The OS page cache turns that append into a RAM write from the producer's perspective. When a caught-up consumer reads, the data is already in the page cache, zero disk reads. And when Kafka ships that data to a consumer, it calls send file, which bypasses user space entirely. Without zero copy, Kafka moved 450,000 messages per second at 82% CPU. With zero copy, that jumped to 1.85 million messages per second at just 21% CPU. That's a 4.1 times throughput gain and a 3.9 times CPU reduction from a single OS primitive. In a 2020 Confluent benchmark on i3 en.2x large nodes with Acks equals and RF equals 3, the cluster sustained 605 megabytes per second. That's with full durability, not fire and forget. And let's put the persistent myth to rest one final time. Kafka is slow because it writes to disk. False. Sequential writes go to the OS page cache first, meaning RAM. Caught-up consumers read from that same cache, meaning zero disk reads. The disk is there for durability. The speed comes from RAM and the kernel. Kafka's performance isn't magic, and it isn't proprietary hardware. It's discipline. It's the disciplined application of four primitives: sequential I/O, batching, OS page cache with send file, and partition-based horizontal parallelism, all working in concert. Strip any one of them out, and the throughput story falls apart. Keep all four, and you get a system that scales from a startup's single broker to LinkedIn's 7 trillion messages a day without changing the fundamental design. That's the four pillars: partitions for parallelism, offsets for position, consumer groups for scale-out, and sequential I/O plus zero copy for raw speed. Build with those ideas and you'll understand not just how Kafka works, but why it wins.